In 9.4, we're going to take a look at yet another way to determine if infinite series converge or diverge. And here we're going to be taking a look at two tests that use a comparison to an infinite series we know something about to an infinite series that we don't know something about. And there's two different types of comparison tests that we're going to look at here. And again, I just want to point out, like you heard me say in 9.3, there really is no difference between 9.3, 9.4, 9.5, 9.6, and ultimately 9.7, as this is just a collection of a bunch of tests that help us determine if an infinite series converges or diverges. Okay, the first of the two comparison tests that we're going to look at is called the direct comparison test. And with this test, of course, we need two infinite series so we can compare them. So we're going to consider two series, A, which is positive, and B, which is also positive. So there's two outcomes that can happen with this direct comparison test. So in the first, we have to suppose something about this A and B infinite series. The A infinite series is going to have to be smaller than the B infinite series. But what are these A and B infinite series? How do we even identify which one's which? Well, the way we need to look at this A and B series is this way. A is our unknown series, the one we don't know anything about. Or in other words, it really is the problem that you're trying to solve. Of course, you're going to be given a series and you need to figure out if it converges or diverges. So that would, of course, be our unknown series. Our B series is the known series, and really what that's going to be is some sort of geometric series, or maybe some sort of P series, because those are really the only two series that we know anything about. We know about geometric series, and we know about P series, so that'll be what our known series is. Okay, so once we kind of sort that out, again, we're supposing that our unknown series is smaller than our known series. And what that's going to mean for us then is that if the B series converges, then the A series also converges. And the way I can prove that is with a picture, because I don't think just by saying this alone it's enough to really see this. So let's take a look at this picture. What we're showing here is that we have two series. They're both shrinking. But what is the key here is that the B series and the A series are related by the A series being smaller than the B series. You'll notice here in this picture, the B series is above the A series, so that of course means the B series is bigger than the A series. And what we know here is that if the B series converges, or that is to say, if the B series is shrinking down to 0, then of course the A series must also shrink or converge as well. And again, it's because of their relativity to each other. Since the A series is always below the B series, and again we know the B series is converging, then that must mean, because of that, the A series also converges. So I know that's a lot to take in all at once, but hopefully this picture kind of illustrates what this first scenario is trying to get you to see. I guess the bottom line is I'm going to try to just translate this into English here so it can maybe make it a little bit easier to understand. But if the larger series converges, which is the one we know, then the smaller series, which is the one we don't know, must also converge. Okay, once you understand that, really the other case is just kind of this flipped in a manner of speaking, but that's the idea behind this direct comparison test. We're comparing one thing we don't know to something that we do know, and then we can make a conclusion based on that. Okay, so in this other scenario, we're going to now suppose that our unknown series is bigger than our known series. And in this scenario, the known series, again, we have to know something about it, diverges, which would mean then that our unknown series also diverges. And again, the proof of this can kind of be seen a little bit easy with a picture. If something's diverging, it's kind of growing without ever approaching a particular number. So what we're saying here is that we know our B series, this is the known one here, is diverging, or in other words, it's growing without ever stopping. And the key to this problem is we know the A series is bigger than the B series. So again, based on this relativity idea, if the A series is always above the B series, and again, we know the B series diverges, if that A series is always above it, then of course it must also diverge. Again, kind of translating this into English, if the smaller series diverges, which is the one we know, then the larger series, which is the one we don't know, must also diverge. So again, it's definitely a complicated concept, I suppose, to kind of take in all at once. So again, kind of take your time in trying to understand this, but hopefully with some examples, it'll become a little clearer. Okay, so we need to determine whether this infinite series converges or diverges. I want to kind of, again, model what I think you should always do with these infinite series when you're given them. You should always try to do that nth term test right away because it's a quick test you can use to see if an infinite series converges or diverges. And again, the quick review here is if you take the limit of an infinite series and if you get anything other than 0, you know it diverges. And then you don't have to worry about any of these tests that we've been looking at so far. But, you know, it's kind of a waste to do one like that. So of course, in this case, when we take the limit of our infinite series here, we get 0, which just means we need to try another test. So this is a good candidate for the comparison test because here's the question we have to answer. We need to figure out what the essence is, what the spirit is, what really the bottom line is when we're looking at this infinite series right here. And what I mean by that is since we're going out to infinity, of course this is an infinite series, as we go out to infinity, what really matters concerning our term, our general term I should say, of this infinite series? Well, of course the one in the top matters, there's only a 1 on the top, but in the bottom, does adding 1 really contribute once we're out at infinity? Well, no. Does multiplying by 2 in front of that n cubed really contribute much once we're out to infinity? Well, again, the answer is no. So really what we're looking at here is the 1 over n cubed p series. This series that we have resembles the p series 1 over n cubed. And of course, it's not equal to it. That's the key. It resembles the p series 1 over n cubed. And again, we're thinking about this from the point of view of being at infinity. Again, adding 1 in the bottom really won't affect much, and multiplying by 2 doesn't really affect much. Really what matters is that power of 3. And of course, we know that this is a p series that converges because p is bigger than 1. So now we need to use our direct comparison test. And which of the two cases are we looking to do from that first slide? Well, we're looking to figure out, is our unknown series smaller than our known series? And assuming that's true, then this should kind of work out for us. So really this is just a true-false statement. We're just trying to figure out true or false. Does our unknown series, or is our unknown series smaller than our known series? Because if it is, then they must both converge. And again, this is the first case from that last slide because our known series converges. So that's kind of how we know that we need to set it up using this less than. Okay, so is that true or false? Well, you just need to know a little bit about fractions here. If we reduce a denominator, which is what we're doing right here to this known series, if we reduce the denominator, that increases the overall size of the fraction. So of course that would mean that this p series 1 over n cubed is indeed bigger than our unknown series. And of course if that is true, then that must mean that our unknown series must also converge because we compared it with the known series, or the p series, 1 over n cubed. So, you know, these aren't quite intuitive for sure. It takes a lot of analysis to kind of think about these. So, you know, ironically, that kind of makes them a little bit harder than other problems. There's really not much work to show. It's more the analysis that goes into these problems that really makes them hard. Okay, so just let's keep on doing some examples here. Again, I'm going to do the nth term test, which means I need to take the limit of this infinite series, but you know, I'm just doing this to model this, so you guys will always try this as well. Because if we got anything other than 0, we of course know we would know this infinite series would diverge, but here we get 0, so we need to try another test. And in this case, we're going to use the direct comparison test. The reason this is a good candidate for the direct comparison test is because if we think about this infinite series as we go out to infinity, what really matters? Well, in the top, that plus 1 doesn't really do much, and of course in the bottom, it's only n squared. And if we simplify that, we really just have the infinite series 1 over n, which is a harmonic series, and we know that that infinite series diverges. So that's of course our known series, and since we're looking at the diverging kind of case, we need to figure out, is our unknown series always bigger than our known series? Because if that's true, then both of them diverge. And again, this really just comes down to how you view or what you know about fractions. You'll notice in our unknown series, in our known series, the numerator is decreasing, which would mean the overall fraction also decreases. We can look at this in a number of different ways, I suppose, but bottom line is you could also just plug in some numbers for n and see which one is bigger or smaller, if looking at it this way is kind of confusing you. And same thing when we did over here. You could always just plug in some numbers for n and see if one is bigger or smaller. But bottom line is, we know that this is a true statement. The known series is smaller than our unknown series, which means that by this direct comparison test, this unknown series must also diverge because we compared it to this harmonic series. Okay, one more example here. Here, I'm not going to even bother using the nth term test because it really wouldn't make sense to. We'd have 3 to the infinity in the bottom, and we're not really sure how to deal with that. But luckily, we know that this kind of looks like something. The first two examples, the essence of our problem was really of a p-series. In this problem, of course, the 2 in the bottom doesn't really do much, so this really looks like the series 1 over 3 to the n. And if you recall, I didn't animate this in this PowerPoint, but if you recall, this is really 1 to the n over 3 to the n, which is then in turn equal to 1/3 to the n. So kind of keep that in mind. Don't forget about that little algebra trick here, because bottom line is this resembles a geometric series where r is equal to 1/3. And if r is equal to 1/3, then we know that this geometric series converges. So our known series converges. So that means we need to set up this situation right here. We need to see if our unknown series is less than or smaller than our known series. If that's true, then both series behave the same way. And again, you can kind of just take what you know about fractions. On this unknown series, or actually I should say on the known series, let me change that here. On the known series, we're reducing the denominator. We're taking away that addition of 2, so that would increase the overall size of this fraction, which is good because we need this known series to be bigger than the unknown series. So this is definitely a true statement. And since it's a true statement, we can kind of keep this a little simpler. I know up here and up here I wrote a very long statement out. I just wanted to be very clear about what was going on here, but I'm going to kind of keep this one real simple. We're just going to say that this infinite series converges by the direct comparison test. Okay, I have a feeling that for a lot of you, the direct comparison test, just like many Cal 2 students, will probably be not your favorite test to apply. So luckily, I think for a lot of you, if you ever have to do a comparison test, I think for most of you, you'll pick this limit comparison. And I think the main reason will be is that there's an actual process to follow. I think what makes the direct comparison hard for a lot of Cal students is that there's a lot of analysis you have to do and not much math steps. And fractions are also an issue for a lot of Cal students, so that's why the direct comparison is usually not a popular one. But this limit comparison can be done instead, not all the time, but luckily if you have that opportunity, I think you'll probably choose the limit comparison over the direct comparison. So same thing goes. We have two series, one where we know something about it, one where we don't know something about it. So what are we going to do for this limit comparison? Well, what we're going to do is we're going to take the limit of a fraction. And that fraction is going to be the unknown series over the known series. And if you get some number, this L right here is just some number. It can be any number, as long as it's some number between 0 and infinity. It can be equal to infinity, of course, but as long as it's some number, then we know something about the unknown series. The unknown series either converges or diverges depending on what we know about the known series. In other words, I'm kind of saying this the long way, both series behave the same way. Okay, so that's really all there is to it. It's kind of the same idea that we were looking at from before, but now we're actually going to do a math problem, a calculus limit problem, and not just look at two fractions and see what happens. So here we want to figure out, does this infinite series converge or diverge? And if you kind of take away what you saw on that last slide, what is the essence of this series? Well, in the top we just have the 1, of course, and in the bottom, once we go out to infinity, adding 1 isn't going to do much. So this unknown series, and here's the key, resembles this p-series right here, the 1 over n squared p-series, which we know, luckily, if we remember our knowledge from 9.3, we know that this p-series converges. So we're not going to set up some inequality and trying to figure out which fraction is bigger or smaller. Here we're going to take a limit of a fraction. And that fraction is going to be the unknown series, the 1 over n squared plus 1, divided by the known series, 1 over n squared. Okay, so I hope you don't want to take the limit of this as it looks right now, because what we're going to do, since we're dividing by a fraction, is do a copy change flip or a copy dot flip, if that's how you were taught it. We're going to take that 1 over n squared and flip it to the top of that fraction. So we'll end up with n squared over n squared plus 1, and that we can certainly take the limit of. The limit of that is just equal to 1. We got a number, and that's all we really care about. What this tells us is, since this limit is positive and finite, it's a positive answer and it's not infinity, then we know both series behave the same way. And again, since we know that our known series converges, then that must mean our unknown series also converges. So I'm going to write this answer out very, very clearly. Since 1 over n squared, since that infinite series converges, then we know our unknown series must also converge. And I'm going to kind of start being clear about my answers. We need to kind of always round out our answers with what test we used. So since we had these two comparison tests, I want to be clear here and say that it converges by the limit comparison test. So that's going to have to be something we start kind of doing every time we write down an answer. Let's go ahead and put what test we used to verify the converging or diverging. Okay, one more example of this. Again, we need to find the essence, the resemblance of this unknown series. Again, in the top, adding 1 won't really do much, and in the bottom, subtracting 1 and multiplying by 3 ultimately don't do much once you're out at infinity. So ultimately, our unknown series looks like this series, n over n cubed. But of course, we can simplify that to be 1 over n squared, which is exactly the same infinite series we saw in this first example here. So that's good. We know, again, that's a p-series. Since p is bigger than 1, that p-series converges. So now we can apply our limit comparison test. We need to take our unknown series and divide it by our known series, which is 1 over n squared. Once we do that, we can try to evaluate this limit. And a lot of the times, actually probably almost every time, you're going to have to do this. You're going to have to take that bottom fraction and flip it from the bottom. Or in other words, when I say flip, I really mean multiply by the reciprocal. Of course, n squared over 1 the dividing by 1 doesn't matter, so we need to multiply the top, that blue n plus 1, by n squared. Next, we need to take the limit. In the top, we need to distribute this n squared to make the limit a little bit easier to do in one step. So we'll end up with n cubed over n squared. So what is this limit equal to? Well, when we take this limit, we're just left with 1/3. And that's great, because that means both of these series behave the same way. Since the limit turns out to be a positive finite number, we know the series behave the same, so we can make a conclusion now. We can say that since our known series converges, our unknown series must also converge. And again, we're going to have to kind of start getting into the habit here of saying what test we use. So we're going to say that this unknown series converges by the limit comparison test. Okay, in this last example, this is a very specific AP test kind of question here. Not that the other ones aren't, but this one's a very specific kind of AP kind of practice problem. And really, I think what makes this a very unique problem and why it's kind of an AP kind of test problem is that they kind of take the numbers out of the problem. I think for a lot of you guys, you're used to these kinds of problems where usually there's a number here for P. It's not just the letter P, it's like a 2 or a 3 like you saw maybe in that last slide when we were doing those examples. But here they kind of take that number out and they still want us to figure out whether or not some things are converging or diverging. Here though, it's not quite the case. They're telling us that this infinite series does converge, and we want to figure out what values of P it converges for. Okay, so I guess there's something we should first do, and it's really for the sake of practicing the limit comparison test. Let's at least see, does this infinite series converge or not? And then we'll talk about the values of P that it converges for. So what is the essence of this series? Well, in the top, of course, there's just an n, and in the bottom, when we go to infinity, adding 1 doesn't really do anything, so we're really just looking at the series n over n to the p power. So again, this bottom part right here, everything that I'm about to do right here, I'm only doing just to practice the limit comparison test. We already know that this infinite series converges. There's really not a point in doing this, other than the fact that it's a good idea to kind of practice this limit comparison test since it's so new. So let's go ahead and do the limit comparison test. We have to take our unknown series, which is again our original problem, and divide it by our known series, which is over here. And we actually don't even know what kind of P series we're dealing with here. We just know that this unknown series converges, so we're again going to use this limit comparison test. Okay, so we kind of have a mess here, so every one of these problems usually works out to be one of these where we do a copy, change, flip. So we're going to take the top fraction and multiply it by the reciprocal of the bottom fraction. When we do that, of course, we can kind of simplify here. The n's will cancel here, and then we're just left with n to the p divided by n to the p plus 1, and that we can take the limit of. If you kind of disregard the plus 1 and take this and simplify it, which would just be equal to 1, when we take the limit of 1, of course, that's equal to 1. And because of that, we know, because we have a limit that is positive and finite, both series, and what do I mean by both series? Both of these series right here behave the same. So if we know this unknown series converges, then we also know the known series converges, or vice versa. Okay, so technically, in a sense, we didn't have to do all that, since they kind of already told us our unknown series already converges. Again, I just wanted to do that for the sake of practicing this limit comparison test, but at least we can verify that both of these series are going to converge, or they're both going to behave the same, is really what I should say. Okay, so now let's get to the part that really matters here. What is this thing doing, or what is this series, so we can figure out where P, what values of P it converges for. Well, there's a couple things we can do here algebraically. We can rewrite this as 1 over n to the p, and if I take this n to the first power, there's an invisible 1 right there. Let me make that a little clearer. There's an invisible 1 power right here on the n. we can of course send that n down to the bottom as an n to the negative 1 power. The reason we would want to do that is if we multiply those two n's, then we add their powers, which would just be p minus 1. And this we should recognize. This we should recognize as a p-series. Anytime we have 1 over n to a power, that we know to be a p-series. And we know a p-series converges when the power is bigger than 1. Just like whenever we had 1 over n squared, that converged, because p was bigger than 1. But in this case, the power we're looking at is p minus 1. And again, we want this p-series to converge, so p minus 1 has to be bigger than 1, and this is a very simple inequality to solve. If we add 1 to the other side, it turns out that the values of p that make this converge are the values of p when p is bigger than 2. So a very good illustration of a limit comparison test, and then on top of that, taking what we know about p-series and applying that with regards to this limit comparison test.